You know that feeling when you look at your calendar and it's just a total disaster? Packed with overlapping meetings, jumbled appointments? What if you could take all that chaos and, in seconds, just snap it into a clean, simple schedule? Well, that's the magic of the merge intervals pattern. And trust me, this idea is fundamental. It's powerful. And you're going to find it everywhere, from coding interviews to the very core of systems you use every day.
So here's our game plan for this explainer. We're going to start with the problem itself, a total mess of overlaps. Then we'll uncover the one single insight that makes the whole thing click. After that, we'll walk through the actual method step by step, figure out why it's so incredibly fast, and finally, connect the dots to see how this simple algorithm is a total workhorse in the real world. Let's dive in.
All right, first things first, let's get a really solid handle on the problem we're trying to solve. At its heart, this is all about taming chaos.
We've all been there, right? You've got a meeting from 9 to 11 a.m. Then another one gets booked from 10 to 12, and maybe a quick check-in from 11:30 to 1. If you look at that, it's not really three separate things. In reality, that's just one solid block of work from 9 a.m. to 1 p.m. Our goal is to get a computer to see that, to find those consolidated blocks all on its own.
And here's what that mess looks like as raw data. Just look at it. They're completely out of order. Meeting C, which is from 1 to 3, actually starts the earliest, but it's just sitting there third on the list. You and I can probably spot that meeting C overlaps with meeting A, which is from 2 to 6. The real question is, how do we teach a machine to reliably see that and merge them into one clean interval of 1 to 6? This is the jumble we need to sort out.
So, how in the world do we tackle this mess of numbers? You might be thinking it's going to take some complicated formula, but it turns out the solution is a single, almost shockingly elegant idea.
And this, right here, this is the aha moment. When you're faced with this kind of disorder, what's our most basic human instinct for making sense of it? We put things in order. And it turns out that instinct is exactly the key.
That's it. Seriously, that's the whole secret. By just sorting all of these intervals based on when they begin, we totally transform a chaotic puzzle into a simple, straight line. Once they're in order, all we have to do is just walk through them one by one. Okay, now that we've got our core insight, our secret weapon, let's build the full algorithm around it. It's a classic two-step process. First, we organize everything, and then we process it.
So here's exactly how it works. First, like we said, you sort all the intervals. Simple enough. Next, you just create a new empty list to hold your clean results. Step 3 is where the real magic happens. You scan and merge. You just walk through your sorted intervals, comparing each one to the last interval you saved. If it overlaps, you just stretch out that last interval to include the new one. If it doesn't overlap, well, you close out the old one and start a new one. And finally, don't forget to add that very last merged interval to your list.
Now, this strategy actually has a formal name in computer science. It's a greedy approach. And it's called greedy for a reason. At every single step, we make the choice that seems best right at that moment. We greedily stretch our current interval as far to the right as it can possibly go. And the only reason we can trust this to work is because we sorted everything first. That simple act of ordering lets us be sure that each small greedy decision builds up to the perfect final answer.
Okay, here is a super important detail you have to consider. What happens if two meetings don't really overlap, but they touch perfectly, like one ends at 2 p.m. and the next one starts at exactly 2 p.m.? Should they become one big meeting? You know, there's actually no single right answer here. It totally depends on what you need. The key is to make this a deliberate choice, a policy you decide on before you start coding.
So, we've got a method that's simple and gets the right answer. But, is it fast? Let's talk performance, because in the world of algorithms, efficiency is absolutely king. Here's the most important thing to understand. That first sorting step is the bottleneck. It dictates the overall speed. For a typical unsorted list, the time it takes is what we call O(n) log n, which is pretty much the gold standard for sorting. But, and this is a big but, if your data is already sorted when you get it, then you get to skip that whole step, and the process becomes a blazing fast linear scan, or O(n). It just zips right through.
All right, let's talk about a few common traps people fall into with this one. As we just discussed, forgetting to decide on that touching rule is a classic bug, but another huge one is trying to sort by the end time instead of the start time. If you do that, the whole greedy logic just breaks down. You can't trust that the next thing you see is the right thing to merge. These are exactly the kinds of little details that interviewers love to see if you catch. It shows you're thinking about the edge cases.
Okay, so we've got the theory, we've got the method, now let's bring it home. Let's connect this abstract algorithm to its actual value in the real world. Where are you really going to see this thing in action?
The applications are, and I'm not kidding, everywhere. Yeah, calendars are the obvious one. But operating systems use this for scheduling tasks on a CPU. Network routers use it to merge firewall rules. Financial systems use it to compress windows of time series data. Even in bioinformatics, scientists use this exact pattern to merge overlapping gene segments on a chromosome. It's a true workhorse.
And here is a fantastic piece of advice for any coding interview. Before you type a single character, just ask, quick question, should we merge adjacent intervals, like one that ends at 2 and one that starts at 2? Asking that immediately shows you're a careful, thoughtful engineer. It's such a simple question, but it proves you think about the tricky bits before you start, and that can make a huge positive impression.
Now, it's also really important to know the limits of this pattern. Our sort and scan method is perfect if you've got a fixed list of intervals and you just need to merge them once. But what if your intervals are constantly changing, being added, removed, updated all the time? Resorting the whole list every single time would just be way too slow. For that kind of dynamic problem, you'd need to level up to a more advanced data structure, something like an interval tree.
So there you have it. We've seen how one incredibly simple idea, just sorting, can take a chaotic problem and turn it into an elegant, efficient solution. It's a perfect example of the power of bringing order to data. And that really brings us to a final question to think about. This simple scan is great for merging intervals, but what other kinds of questions might we want to ask about our data? And when would this simple, powerful approach just not be enough?